All right. All right. So we're going to talk about kinematics. Kinematics, okay? Study of motion, all right? We need to start with some basic concepts. And we're going to start with vectors. And if I look at, there's three different vectors that we're going to start with. Displacement. Velocity. And acceleration. Okay. They have a counterpart. Displacement has a counterpart of distance. Velocity's counterpart is speed. And there really is no counterpart necessarily for acceleration. Okay. You could call it acceleration, but you could say that if you want to. The difference between the right column and the left column, Tucker, you should probably be taking notes, kiddo. Guys, this is no time. The difference between vectors and this right column, they're called scalars. Does anyone know what I mean between vectors and scalars, what the differences are between the two? Anyone have an idea what the differences between scalars?
There's something with scalars and like math.
Mm-hmm.
But I don't know what it is.
Okay. Anybody else have an idea? Thoughts? Okay. A scalar is essentially a magnitude. Okay, it's an amount, like an absolute value. Okay. A vector is a magnitude plus a direction. Okay? If I told you that Dallas was 45 miles away, is that going to help you get to Dallas? Because Dallas is over here. What's 45 miles west of us? Like some other town? That's north. Huh? Brock, sure. Let's call this whatever, question mark Texas, right? Okay, here's Dallas, Texas. Okay, and here's Fort Worth. Have to have a hat, right? Texas, okay?
I don't know why that's specifically Fort Worth.
Because we're very.
You didn't finish that sentence.
Okay.
You need to shade the hat, Mr.
What?
You need to shade it.
Shade it. Oh yeah. Okay. The sentence is telling you that it's 45 miles away doesn't help you. You need the magnitude, which is 45 miles, the distance, but you also need direction, 45 miles east to get to Dallas. That is a vector. It's a magnitude and a direction. Okay? Happy.
Yeah, I understand like how displacement and distance work as like a difference between like a vector and a scalar, and I understand how acceleration can't be like.
Well,
I don't
it is.
understand like velocity.
We're going to get there. I'm going to go through them one by one. And I don't know. We'll see if you truly get it. I hope you do. But let's talk about what the difference between distance and. We're going to start here today. It's really acceleration, but it's not really. There's no other term for that I can think of, and maybe I'm just not thinking. But there's no other term that I know of that's the magnitude of acceleration. You can have a magnitude of acceleration. It's probably just called acceleration, right?
Makes sense.
Right, but there's a direction. Acceleration has a direction. I can be accelerating forward, or let's say I had a positive acceleration. What does that mean to my speed? Does anyone have an idea? It increases. If I have a negative deceleration, what am I doing? Yeah, so it's like I'm hitting the accelerator pedal or I'm hitting the brake, right? And we'll get to that, and we'll get to that point. But let me just start at displacement, okay? But before I even start there, let's talk about symbology, okay? Lots of things are vectors, okay? So velocity is a vector, but when you write velocity as a vector, the official way to write it is with a V and an arrow over it. That arrow denotes that it's a vector. Okay? Its scalar of speed is s. Okay? Displacement would be D, a lot of times capital D, but lowercase d or whatever, but with a vector versus lowercase d for distance. Okay? Force, acceleration, they're all vectors. So you should know on a quiz, hint, 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 that if I have an arrow above it, that's a vector versus something without an arrow. If I had acceleration, velocity, force, these are non-vectors. These are just magnitudes. They don't have direction. Okay? That's how you technically write a vector. Now, I'm going to apologize up front. I'm going to be writing these things all the time. We're going to be writing F, V, D, A, all of that all the time. Now look. 98.9% of the time that I talk about these things, they're going to be vectors. Am I going to write the arrow on top of every letter every time? I apologize. Probably not. Okay, just because I don't have the time, I probably won't remember. Okay, but note that if you see a value with an arrow over it, it's a vector. If I'm talking about force, velocity, distance, acceleration, I'm typically talking about the vector quantity. If you have a question, raise your hand and say, Mr. A, are you talking vector or scalar? And I'm happy to answer the question. The one thing that I will write as a scalar that has no vector, no, speed has a vector equivalent, is mass.
I have a question.
Hold on. When I say mass, the mass of something, the amount of something, has no direction. It's just a mass. There is no vector quantity for mass. So when I say, ultimately, F equals mass times acceleration, the only two vector quantities are the force and the acceleration, not the mass. Mass is a scalar. Does that make sense? Because I can have amount of something but not a direction. Yes, ma'am.
Okay, so if velocity is a vector and its counterpart is
Speed.
then how can you also have a v in the scalar?
Well, because I might, and you're right, because a lot of people will write this the same way. You'll see in both ways. Okay, speed is the velocity scalar technically. Some people may write v without as a scalar, but typically when you see v, it is a vector. So I'm gonna, for your clarity's sake, I'm just going to erase that because that's a good point. Okay. All right. Cool. Cool. All right. So are we good with that? Any questions? Okay.
What's the capital F on the
This is force.
Is that the same as scalar? Scalar sign?
Yeah, it's a scalar. It would be a scalar force. Like I could say I have 2 newtons of force,
Yeah.
but typically when we say 2 newtons of force, we imply a positive 2 newtons. But then you got to decide what direction positive is. So there's a lot of nuances. Then we get through this, you'll get this. But I just want you to be clear. What I really want to get out of this is that if you see an arrow, you know it's vector. Technically, a vector should be written with the arrow above the variable. Okay. And the fact that the difference between a vector and a scalar, is one has direction, one does not. Right? Okay. All right. Let's talk about a very simple thing. Let's talk about if I started here and I started to walk, run, jog, crawl, squirm, okay, to this position here, okay, where this is my start and here's my stop. And let's say I went 5 meters up, 10 meters to the right, and then another 5 meters down. How far have I traveled? How far have I traveled from the beginning to the end?
1 meter.
Everyone? 20 meters. This is my distance. My distance is how far I went. This is 20 meters. Notice it is just a magnitude, no direction. Okay? However, what would you think my displacement is?
Is it broken up into 5, 10, 5,
Meters
2?
up, 10 meters
Close.
to
Say again?
the right. 5 meters up and 10 meters to the right and 5 meters down.
So it'd be 15.
Not necessarily. Okay, you're on the right track. You're both on the right track. I don't know where your math was, but I think you're on the right track. I think you just did the math wrong. But here we go. The displacement. What did you guys say? 10. Okay. So I'm going to write I'm going to draw a displacement vector.
I have my math wrong.
Yep, that's it. Yep. Displacement vector from here to here. Here's my displacement vector. And that displacement vector is, here's my displacement. And that is 10 meters. And am I done? Is that the answer? No, what's that? What am I missing?
+5 and -5.
Nope. 10 meters is the length of this line to the right. I've got to show some sort of direction. Okay? I can say to the right. I could say another number of different ways. So the length of this line is the scalar part. It's 10 meters. The direction you could do it a number of ways. This is one way to do it. Might be to the east. Does that make sense? Everyone knows north, west, south, east, northeast, west, north, south, east, west. Yeah, I've heard this. I've only heard 3 of them today, but never eat soggy waffles. I don't like that because it's like, is it never eat soggy waffles or is it never eat soggy waffles?
It's like wheat.
Yes, I like wheat. Yes, and that's how I remember. The W spells out the word we or wees, right? But we, right?
I learned it never eat sour worms.
But is it never eat sour worms? Is it never eat sour worms, right?
It's like
Yeah.
a claw. I just remember north, south, east, and west.
That's good. As long as you guys know. As long as you know which is which. All right? Okay. So that's one way of doing it. You could say to the right, okay? But that assumes that you're facing up is this way and right's that way. What if you're facing that way? Well, right's that way. So you have to be very careful about how you describe this because what? Did what I just said totally?
It said never eat sour water. That's what I like.
That's fine. Okay, there's a million ways to do it. Let's move on.
That's a watermelon sometimes it is.
Yeah.
I like it that way too.
Okay. All right. Okay, so here's the thing, but let's look at this. Let's look at this from what you guys were talking about, Amr and Divya and Avery. Here's the thing, okay? I'm going to say that what I did was initially I went 5 meters north, then I did what? 10 meters, east, east. And then I went 5 meters south, right? Now, if I took the north, east, west out of this room, because it's kind of difficult to see, but you know that the north cancels out the south, right? So really what I did was I did -5 meters in the north, right? -5 meters in the north, which negative north is really south, right? So in the end, they cancel out, and I'm left with positive 10 meters in the east direction. Okay, we're getting it. Good thought. So, what was your question, Antonio?
We have to do that every time we find.
No, well, not unless I ask you for it. Okay, but here's the other thing. I'm going to draw it a different way. Okay, the other option, in reality, okay, is like this. Got.
So is it best to just stick with like a north and an east or like a south and a west and not put all 4 in there? Because they're like opposites of one another, so they'll cancel out.
Let me show you. I'm going to show you a different way. Yeah, and here's I'm going to show you a good way of doing it. You can do it however you want, right? As long as we're clear. But typically, we're going to be using x and y coordinates. Okay, everyone knows the x and y, right? This is my origin here, where I start. To the right is typically positive. To the up is typically positive. To the left is typically negative. Down is typically negative, right? Okay, so I could say I went positive 5 meters in the y. I then went positive 10 meters in the x. Then I went negative 5 meters in the y. And that's where I stopped. So you see how I'm separating them like that? Mm-hmm. And now I can add them up. And I say 0 meters in the y and positive 10 meters in the x. Does that make sense? And this kind of can help you do this. Now, here's the interesting thing. Notice that I can move up and down the y. Did it have any effect in how far I went in the x? The motion in the y, this is important to note, and that you'll get this a little later on here. The motion in the y is completely independent of the motion in the x, and vice versa. Let me explain what I mean by that. Okay? Avery, I'm going to toss this to you, okay? I'm going to toss this to Avery a couple of ways. I'm going to toss it really, really big, okay? All right, so you caught that, toss it back. Okay, and I'm going to toss it back to her. It's going to get to her at the exact same time, but notice the amplitude. Okay, it's a little lower. But if I get to her at the exact same time, the motion, the speed in the x direction, is it different?
Yes.
No.
Wait, yes it is.
In Y.
No, it's
Because
not.
we tossed it up, it
In
took
Y
longer than
direction.
But if it takes the same amount of time for me to toss it horizontally at you. Let's do this. Let's do this. Ready? Okay.
It's like
Yep.
a parabola.
Yeah. Right, when I do this. Okay. Let's assume it got to the same time. Okay. All right. And there's a way of doing that, but the motion in the horizontal is independent of my vertical. Okay. So we'll get more into that. But right now, notice that my distance that I travel in the vertical is independent of my horizontal. Okay? Let's try another one. Are you ready?
Sure.
Oh, let me come back here for 1 second. Let me do one more thing. Notice, by the way, let me just make this real quick clear. Notice that this big orange final vector, the net displacement vector, is made up of the summation of 3 smaller individual vectors. Right? The vector of positive 5 meters in the y, the vector of positive 10 meters in the x, the vector of negative 5 meters in the y. And adding all of those vectors up gives me the net vector of displacement.
So it's really just showing that she could have, or whoever we're talking about,
Yeah.
could have just taken the yellow.
Yes. If we're independent of time right now, we're not talking about time, we're just talking about getting a distance, okay? Getting from one place to the other. You could have gone, to your point, from here right to there, or you could have gone here to there, right? You can get home 3 different ways, right? Your time may be different, but you can get them home 3 different ways. One might be shorter than the other, okay? But what I also want to note is that when I say plus 5 meters in the y and negative 5 meters in the y, these are 2 different vectors. They're the same magnitude, but the opposite direction. So if I took this up arrow and that up arrow and I add them together, I get 0, right? Does everyone see that? Sean, are you with me? You guys all see this? Okay. This is important. It's basic, but it's important. So let's say I start here, okay? And I go here, and I go here, and I go here, and I go here. And let's say that I go 3 meters, 7 meters, 3 meters, 7 meters. Okay? What is my distance that I traveled?
20.
Everyone? 20, right? 7 plus 3 is 10 plus 2 times 2 is 10 meters. What is my displacement?
0.
Okay. 0 meters is my displacement. Do I need to give you a direction at that point?
No.
No, because I haven't gone anywhere, so this direction is kind of meaningless at this point. Does that make sense? Okay. If I started here, okay, and I ended here, okay, but I did, yes. What is my displacement? What draw my displacement vector? Where would it go? From where to where?
Just like across.
From the start to the end. That's my displacement vector with the arrow pointing towards the location I end up with. If I were to literally add up all these individual vectors, up a little over, up again, up at an angle, back down another angle, blah, 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 blah. If I add them all up, I would get this vector right here. Does that make sense? Okay. I'm going to give you an example on Monday. Oh, by the way, I'm going to be giving you guys a reading assignment. Shh. I'm going to be giving you guys a reading assignment.
Is it one of those really long ones?
Hopefully not. Hopefully not.
Remember one time I got one and
That's not what I want. I want, where the heck am I? You what? I don't know where my, there it is. So I'm going to give you a reading assignment in the physics classroom, okay? You'll need to have that for Monday, okay? Tomorrow we'll be working on your project. You will be working at a schedule. You'll be scheduling out the things you got to do. And Friday I'm going to demo the laser cutter for you guys. Ooh. But Monday this assignment will be due to read. And I like the physics. You guys have read this physics classroom before, right? You guys have all. Do you like it?
it just, once they use their examples, it gets really confusing.
But the examples are good. You have to be careful. Those questions are good. Now you have to be careful. Sometimes there are things I'm going over that, or I'm asking you to do that they don't divide out, and they've got a lot of stuff in there. So you have to be careful about what. Make sure you look at the topics that we've covered, because some things are a little bit beyond. So just keep that in mind. And if I give you sections, beware of the sections that you read through. Okay. All right. So now, what if I started here? Okay. And this is Tucker's question. I ended there, or started here and ended there, right? Now, and let's say I went 3 meters up, 4 meters to the right. What is my displacement?
The hypotenuse.
The hypotenuse. The displacement vector is my hypotenuse, right?
Five
Okay. And that number is 5 meters. Does everyone know how we got 5 meters, besides just knowing it? Do we know how to get them mathematically? Okay. Pythagorean theorem. A squared plus B squared equals C squared. But only because what is specific about this triangle?
It is a right triangle.
It's a right triangle. Okay? Shh. Quiet. So I have 3 squared is 9 plus 16 equals 25, right? So C squared equals 25, C equals 5, right? We're going to be doing a lot of this. Be prepared.
We're gonna be
Okay.
getting into like square roots and everything. It's gonna be like whole numbers.
Yeah, you're going to get square root. You have to square root and get a decimal. You're gonna round.
Okay.
Like square root of 17, you may have to do that.
We have calculators.
You have calculators. You have the technology. Okay. All right, now look. Here's the thing. So if my displacement vector, okay, displacement is 5 meters, and what's my direction?
Northeast.
You could say northeast. Well, that's pretty darn vague, right? I mean, if it was 5 miles and I was off a little bit, it might be a bit farther. Now, let's figure. Okay, so you might use an angle, right, to help you measure this. So if I look at, again, if I try and put on here an XY coordinate system, okay, and again, here's my Y and here's my X, okay.
Are we doing the slope?
Sort of. We're getting into the slope is the tangent, but the slope is a hypotenuse, by the way. That is a slope. But we're going to look at this theta. Theta 1. I'm going to call it theta 1 just because I'm going to do another theta in a minute. So the angle that I could say, hey, you know what? You're going to go 5 meters, but you're going to go theta degrees from the y-axis. Okay? Do you guys see that? Theta degrees. Does theta confuse you guys?
No.
Does everyone know what theta is?
Just like a
Angle.
Theta is the same thing as it's a variable. It could be x, it could be z, it could be it's exactly where it is. It could be pink elephant.
Stop it. Stop it.
Get out.
If you're doing it, go.
Wait, I think you need to shave it.
Okay, it's a really horrible elephant. I'm sorry, guys.
That was a bad one.
Okay, so it could be pink elephant, right? It's the same thing. All right. So the point being is that it's just a variable. If I did pink elephant every time I would write theta, I have to draw a pink elephant, and that's just really time consuming. But I should make a little pink elephant macro. Command Shift PE. That'll give me draw PL. Yes. Okay, good question. Why don't we just use X? The problem is there are these standards that everyone sort of gets to. Okay, we have standardly set up that the horizontal axis is X, the vertical axis is Y, and then if I said angle X, and if I said X later in an equation that involved X, then I have two different X's. Does that make sense? And you're confusing which is the angle. You're totally right. But in the end, that's why we're going to use T for torque, T for Tesla, right? And we're going to use all this kind of stuff, or T for torque, T for time. Yeah, there's a million different. Would you please stop? You're being recorded, by the way. Just so you know.
Oh Lord.
Yeah. Okay. Hello. Shout out. Okay. So I've got theta 1. Here's the issue, though. Here's the issue, guys. When I talk about theta, I need to have a direction. Okay? And theta has a direction
It
that
starts horizontally, right? And so that would be.
it doesn't matter which way it starts, except that going counterclockwise, that's positive. It's a positive
Yes.
angle. So when I say in this case, guys, my displacement would be, I'm going to erase this for a second so I can not, okay. My displacement would equal 5 meters, okay, at theta 1 degrees, or negative theta 1 degrees, excuse me, from the y-axis. Do you see why I said negative theta 1?
Yes.
Because I am angling this direction from the y-axis.
Wait, can you just say that out loud?
The displacement, to get from the start to the end, from the circle to the square, I need to go 5 meters at a direction of negative theta 1 from the y-axis. Y-axis, negative theta 1, that's where I turn, boom. Does that make sense? So here's an example. Let's say I had an arrow like this. It's at. Sorry, it's like an at. I'm just saying at. You can write however you want, but look here. Okay, if I've got my arrow, watch this. I gotta turn it theta degrees to the clockwise from the y-axis. Okay? Here's the other thing, guys. I also have another angle in here. My other angle is theta 2, which is from here to here. So I could also say 5 meters, okay, at positive theta 2 degrees from the x-axis. Okay, hold on one thought. Where is theta 2 on this triangle?
No.
Theta 2 is also here. Right? Parallel lines, geometry. We'll finish this up on Monday. All right?
Mr. Ed.